Just awesome. Now, in cryptography, the main purpose of cryptography is to ensure that the communication that you have, the data that you have, or the information that you have, if you give it to somebody else, if you want it to be accessed by somebody else, only that person who is supposed to access the data will be able to read the data in spite of the data being exposed to the public. Okay, that is basically cryptography, the science of hiding information in a way that it will not be intelligible to anybody who is not supposed to read the data. So why do we need crypto? Basically, we need crypto so that we can be able to we can be able to secure our communication. Let me just exit the full screen. So we need cryptography so that we can be able to secure communications. As you can see, even in spite of being intercepted. And by the way, remember, when you communicate with anybody online, when you send information, when you access any resource online, the resource is accessible to the public. And in order for you to prevent that information being accessed and manipulated, or to be legible by somebody who's not supposed to read it, you encrypt it. Okay? So the other thing is confidentiality and access control. The purpose of cryptography is to ensure that you control the people, the number of people, or the people who are supposed to access that information. You limit it, either through passwords, through keys, or through encryption sessions. And also when it comes to integrity and authenticity, the data will not be manipulated, okay? If you want to protect your data, you use cryptography to ensure that once you encrypt the data, if anybody manipulates the data, you can be able to see, it will provide evidence that this data, yes, it has been manipulated because of maybe the original data. There's something with the original data that doesn't match with the manipulated data. And that is through hashing. We're going to discuss them. And non-repudiation. When it comes to non-repudiation, what we're talking about here is a scenario where somebody updates the data or manipulates their data or sends you a file. And then they claim that that file, they are not the ones who sent it. For example, if it's your records, and then they claim that no, they didn't send you that record. In cryptography, you can use that so that you can ensure that the data that you've sent, if I receive it, for example, if it's a bank statement, and if the record is manipulated, even if it's an audio file, if it's manipulated, there is no way, if it is not manipulated, I can say that this file nilikutumia was not manipulated, because the way he sent it to you, once you receive it, there is a process you can use to verify whether the data that you've received from me is authentic, is the same data that you have received. Now, when it comes to some keywords in cryptography, the most common keywords that we apply here when it comes to cryptography is one, the plain text. And the plain text is exactly what you see here. The data that is protected during transmission, the text that is legible, that is intelligible, the text that you can be able to see, that is plain text. And an example here is the document that you're reading, the text that you're reading from this slide. That is pretty much the plain text. The encryption algorithm, this is now the mathematical process that is used to convert plain text into ciphertext to hide that information. And then there's ciphertext. When it comes to ciphertext, what we're talking about here is the end result of the encryption process. Remember, there's the encryption process and there's the decryption, the reverse. So when you have a plain text and you encrypt the plain text, the output will be ciphertext. Now, the ciphertext is the scrambled data, which will not be intelligible to anybody who doesn't have the correct method of decrypting the text and the keys used, or the exact process that was followed. And the exact process includes the key, includes the algorithm and the key. So another thing here, now another thing when it comes to encryption, the other keywords are the decryption algorithm. The decryption algorithm is just the reverse of the encryption algorithm. It is the one that is used to reverse the process from ciphertext to plain text so that it can be intelligible to the person who's supposed to get it or who the data is intended for. The encryption key is the value that is used as a reference for using when applying the algorithm to reverse the data from the encrypted state, which is a jumbled state, to the plain text, okay, to reverse the process. If you want to reverse the process, if I told you that I traveled from here to Nairobi, and I'm telling you I want you to reverse the process, I want to trace back the steps, I must give the directions to where I went. I say I traveled from maybe Roysambu. I went from Roysambu, I passed through Modaiga, I went through Pangani. I must give specifics. And the specifics, that is encryption key. You can jumble up the data, but the process in which you use to jumble up the data, the specific steps are the ones which is the encryption key. Because without the encryption key, all you'll have is the method of decrypting, but how inexact are you supposed to encrypt the data is dependent primarily on the encryption key. And for some algorithms, you realize that the encryption key and the decryption key are different, which is in the public key infrastructure technology or protocols. And for the private key infrastructure, you use the decryption. The public key infrastructure, the decryption key is different from the encryption key, okay? For the private key encryption, which is the normal file encryption, both the encryption key and the decryption key is the same. I'm going to elaborate here. So now this is a typical encryption process. Let me just, let me show you now in a simple to present way. Let me put it as, let me reduce it, fit to width. Okay, let me reduce it to fit to width. As you can see, a typical encryption process, you have the plain text, you have the encryption algorithm, okay, the encryption algorithm. And then from the encryption algorithm, you apply the key to that encryption algorithm to generate the ciphertext, to convert this plain text into the ciphertext. Now, this ciphertext is the one that can be shared publicly, okay? And this decryption process, this is private key encryption, whereby the same key is used for encrypting and decrypting. I'm going to show the differences. Now, as you can see, this data, even when you're performing MITM or man-in-the-middle attacks, this is what you usually see, the ciphertext. You don't see the plain text, okay? But at the end result, at your end node, since you're the one who's browsing, the data that you're viewing when you want to browse any website is the plain text. It is encrypted, and then when it reaches a destination, it is decrypted, and then whatever is presented to you is in plain text. So a simple example is this one. You can see this is hello there, and the hello there uses a substitution form of a substitution algorithm. And a substitution algorithm is like this. D will become A, E will become B, F will become C, D will become A will become D, B will become E, and C will become F. This is the basic way, a basic approach in which you can be able to use it in order to decrypt the data. And as you can see, this is the plain text, the shift, okay? And once you use this, as you can see, this is the algorithm and the key. The algorithm just describes the general procedure, but the key gives you a detailed step-to-step information on how you must derive the original data. As you can see, A is equals to X, B is equals to Y, C is equals to Z. So if you have H here will translate to, this is E. Can you see that? E will translate to, this is B. It corresponds, as you can see, it corresponds on a one-to-one basis. So we've converted this hello there into EBILILQEBOB, okay? This is now how you encrypt data. And this is one of the approaches that were used before encryption, before digital encryption applied. And the purpose of that, as you can, and when it comes to the reasons why encryption precedes, the current technologies was people needed to communicate with others without adversary listening to their communication. And you cannot whisper to somebody who's miles away from you. You need to give somebody that information so that they can relay that information to whoever is supposed to receive it. And the person who you're giving that information, if they can be able to read and provide that information to an adversary, then your communication is compromised and your operations might be compromised. So in order for you to do that in the pre-technology period, where people used to go using carts, the dark ages and whatever, they needed ways in which they could be able to relay information between each other over long distances, but securely enough that if I give you this information, if I wrote it down and handed it over to you, to somebody who will give it to you, that person will not be able to make sense out of it. So even if they copy it, by the time it gets to you, they'll not, whatever you're supposed to get out of that information, you'll get it, and the secrecy will still be maintained. Okay? That was pretty much the origin of how cryptography came about. Now, when it comes to cryptography, there are a few rules that need to be followed when it comes to designing of cryptographic systems. And by the way, when it comes to determining the security of a crypto system, we are not really determining the security here in terms of how you can download something from the net and use it. Sometimes you need to understand how, when it comes to developing crypto systems, how you can be able to secure them. Okay. And the first step here is that the first principle, and these ones, the definition here, or these points, these are just principles that you need to understand, so that when you're developing crypto systems, or so that when you're selecting crypto systems for your applications, you can understand what are the limitations and how best which crypto system can apply to your case. So the first one here is the amount of secrecy required determines the amount of labor appropriate for the encryption and the decryption. This one here means that if your system, if the file is not that secure, if the security level is not that sensitive, if you don't need to, if it's the information is not that sensitive, you don't need to use very complex systems in securing your data. Okay. So that is the first step. The amount of secrecy should correspond with the encryption and decryption algorithm. And the second step is that the set of keys in encrypting and decrypting the algorithm should be free of the complexity of the algorithm and of the key itself. Now, this is what I mean. Now, the key that you've generated, or the key generation algorithm and the way it has been generated, should not be tied to the security of the encryption algorithm or the decryption algorithm. The key that is generated can be generated at random, can be random, but it is independent. It is used by the encryption algorithm, but the way it has been generated should not be tied on a one-to-one basis, but that in a way that you can say, I generated this key this way, so the algorithm the algorithm is affected by this key based on the way the key is generated. No. The way the key is generated, if it's generated 128 bits, if it's used in an algorithm, the security of the algorithm should be independent of the way the key has been generated. Even if the key is large or small, the algorithm should be independent. The security of the algorithm should be independent. The third one is the implementation process should be as simple as possible. Now, what we mean here is that in order for you, when you're building the algorithm, when you design it, it should not be too complex that its implementation is undesirable to people who want to develop crypto systems for their own solutions. The crypto system, the process should be as simple as possible. It should be a step-by-step, simple way to approach, so that when you give the algorithm to a researcher or to a developer, they can understand the whole process and they can be able to replicate it on their own systems using their own language. For example, if I develop a crypto system and I develop my proof of concept, I develop it in Java. If I give the algorithm to somebody else, or even the source code, they can develop it easily using a different language. It should be, the development process should be easy as possible. And now the final part is that the size of the ciphertext should be no larger than the text of the original method. Now here, the funny thing is that when it comes to certain algorithms, this one applies true, especially when it comes to different algorithms, when it comes to block ciphers. And what I mean by the size of the ciphertext, what it means by, if the ciphertext is made out of 5 characters, if the plain text is made of 5 characters, the ciphertext should not be larger than 5 characters. It should be 5 characters max. It should correspond on a one-to-one basis. Reason being is that the text itself, if the final output is larger than the input, then it introduces inefficiencies, and that is something you need to avoid. Yeah, input should correspond to the output, and if you have the output larger than the input, what you might end up with is introducing something called padding. And when it comes to crypto analysis, padding is used. Crypto analysts tend to look at padding, how padding applies, or how the system has been padded, in order for them to generate either a partial key or the whole key, depending on the data itself, or the way the data has been encrypted. So, some factors to consider in cryptography. There is one called confusion and the diffusion. Now, confusion means that the way it generates the key, it should not, not the key, the way it generates the ciphertext, it should not be easily, it should not be easily relatable to the algorithm. So when you generate a ciphertext, when somebody looks at the ciphertext, they should not be able to tell from the ciphertext how the algorithm has generated it. Okay, that is what we mean by confusion. The ciphertext, the way it's generated, when you look at the algorithm, you cannot map it on a one-to-one basis. Even when you use several ciphertexts, it's not easy for you to tell that this ciphertext, this is the way the algorithm generates. And if you can be able to tell that using the way the algorithm generates the ciphertext, then you can be able even to predict how other ciphertext will be developed if there is not enough confusion applied when it comes to the algorithm itself, to generation of the ciphertext. The next one is diffusion. Now, diffusion, there was somebody back in 2019, somebody who developed an algorithm and wanted it to be analyzed for its security. Let me explain the definition and then explain that case. Now, when it comes to in diffusion, if you have A as the plain text, and then you encrypt the text, it becomes something like A, B, C, or C, D, E, and then you change a single character from A to B. The change in the output ciphertext should be so profound that you cannot be able to, if you change a single character, it's like everything else changes. The ciphertext changes, the whole ciphertext changes, okay? So the problem is that when some people develop algorithms, if they change one single character, when you look at the ciphertext, you can be able to see that all other characters have remained the same, but that single character of which you have altered is the one that changes. Now, when it comes to diffusion, what it means that a single alteration of the plain text creates a significant change in the final ciphertext. So if you change one character in the plain text, the whole ciphertext changes. Okay, are we clear to there? Guys.
Yeah, sounds clear.
I need your nice. Now let's go to the classification of encryption algorithms. Now we can classify them using bijection. As you can see, it's a one-to-one corresponding between the function, between the elements, between the function elements between the two sets, where one element is paired exactly with one element in the other set. Okay. Correspondence by how the function has been designed. Okay. And And bijection, you can think of it in a way that, for example, if I develop an algorithm that is purely that applies bijection in its strictest term, the algorithm that will be used to decrypt the plain text is not what do you call it? It's not procedurally commutative. This means if the process goes from A, B, C, the steps, when you reverse the process, it should be C, B, A. Okay? It's non-commutative. Non-commutative just means you cannot have a process. You start by A, B, C, and when you want to reverse, you reverse C, A, maybe like that. You reverse in a random way. So bijection should be a one-to-one correspondence between the function that is used for the encryption and the other one that is used for the decryption process. I'm going to show a few examples here so that we can be able to understand how some things work. The keys used. The first one is the bijection of the function. The other one is in terms of the keys used. Now, when it comes to the keys used, we have two types of algorithms: the private key encryption algorithms and the public key encryption algorithms. In the private key encryption algorithms, the key that is used to encrypt the data is the same key that is used to decrypt the data. And in public key algorithm, the key that is used to encrypt the data will be different from the key that is used to decrypt the data. And I'll show you why this algorithm is used and how they apply to each other, especially when it comes to browsing the net. So there's the encryption mode also. Now the encryption mode, this is now like block encryption, block ciphers, and stream ciphers. Block ciphers are best used for things like files. And when you use block ciphers, the best case for using block ciphers is in data that you can be able to tell beforehand the size of the data. Okay. For stream ciphers, you cannot tell the size of the data beforehand. So you encrypt as you go. You encrypt as you go. You encrypt as you go. But for block ciphers, you know the data is 10 MB, and then you can use one algorithm to encrypt that whole data once. Okay, that is now what we mean by block ciphers and the application of block ciphers and stream ciphers. For block ciphers, the data is split. Even the encryption process can be split into chunks of unique chunks of equal sizes. But in stream ciphers, the funny thing when it comes to stream ciphers like A51, the encryption itself, when you see the data, when you see the C file when you download it from Android, you see that it encrypts based on a chunk of data. But it encrypts continuously until it receives the signal indicating that this is the end of transmission. Okay, and the end of transmission can be 001. That can be or in hexadecimal 01, meaning, or 00, meaning the end of transmission of the data. Okay, so in block ciphers, you'll know the size of the file, and then you'll encrypt it based on your prior knowledge on the size of the file, so you can split it and encrypt it. But in stream ciphers, you don't know the size of the data, so you encrypt it as you go until you receive a signal telling you that this is where the transmission of the data has ended. As you can see, we have talked about that. I've just explained that classification by bijection, mode of operation, stream-based and block-based. And now let me also explain asymmetric and symmetric. Now, let me give you an example so that you can understand how it works when it comes to the internet. In a metaphor, in normal metaphors, for example, I am supposed to contact Jones. I'm supposed to send Jones, we are supposed to initiate communication, Jones and I. Jones maybe lives in Rongai, and then I live in maybe somewhere like Kiambu. Now, in order for me to initiate communication, secret communication, or we want to exchange packages secretly, we need to find a way in which I need to give Jones, we need to share a common key, whereby if I lock my box and I send the box via Matatu to Jones, even anybody in the Matatu cannot be able to unlock the box. It's only Jones who can be able to unlock the box. So in order for me to send that key that John will use, in order for us to agree on one key that we're going to use for the box, like a padlock that has, assuming I send Jones, I want to send Jones a padlock and a key, okay? And I remain with a spare key. But if I send the padlock and the key together where anybody can be able to access it, people can generate their own keys. They can duplicate the keys. So I need to figure a way in which I can be able to send that key and that padlock to Jones, so that when we encrypt, when we share content together, nobody can be able to unlock the padlock, unlock the box. Now, what I'll do is that I'll use a box, the same box, but I'll have two keys, okay? One key will be used to lock the box. The other key will be used, key A will be used to lock the box. Key B will be used to unlock the box. It is only I who will remain with my own key B. Jones has a padlock, has a similar padlock with two keys. One of them is to lock, the other one is used to open. So what I'll do is that Jones might initiate the communication. It depends on who initiates it. So if I'm the one who initiates it, I will do this. I will ask John, please send me, I'll ask him in front of people, please send me that box and the key to lock that box so that I can put something inside that box. Jones will send me the padlock open, the padlock as it's opened, the box is open with the key to lock the box. So once I receive the box, anybody who replicates that key, John can send the same key to everyone, anywhere. So once Jones receives the key, once I receive the key and the padlock, the lock from Jones, what I'll do is that I'll put a padlock. And that padlock, I'll have one spare key, and Jones will have another spare key for that padlock, the secret padlock. Now I'll lock that box, I'll lock the padlock, the secret padlock inside John's box with John's locking key. And then I'll send it over to him, either using public means. Once Jones receives that box, only him can be able to unlock the box and retrieve the padlock. I can even give the Jones key to anybody, so that when that person receives the box, they can put something inside and lock the box, and only Jones will be able to open it. Now, that one is now the public key. Jones secret key, the key which Jones will be using to unlock the box, is his private key. Okay, and the key that Jones will send to anybody so that they can be able to put in anything inside and lock the box, that is the public key. Are we clear up to there? So once Jones has sent me the box, once I've put my padlock inside, the padlock that I bought with one key to either to open and to close it, I'll remain with one spare key and send off that padlock with another key to Jones. And I've locked it inside that box. Now, once Jones receives it, he will unlock the box using his private key. And then once John sees the padlock that we have bought for us sharing our content, now any information that we send towards each other, again, will now use the padlock that I bought with one key that is used to lock and to unlock. Now that is how the web browsers work. Now, this is what happens in browsers. In browsers, if you want to access a remote resource, in either you want to access a remote resource which is secured using SSL or TLS, transport layer security, you are given a public key for the server, the service. The server and the service will send you a public key. That public key, you will generate your own private key that you're going to use to communicate with that server. Only you and the server will have your own key. Once you generate that key, you will encrypt that key using the server's public key, and then you'll send it over via the open internet to the server. Now the server has its own private key for that public key it sent you. Now it will use that private key it had to decrypt the message and see that this is the key that Mike and the server wants to use, my browser and the server wants to use. And then going forward, it will resend that key, confirming that, is this what you wanted to use? And then if I confirm, now every communication that every other communication that I'll be having with that server will be using that secret key that we have defined between ourselves. So that is how symmetric is used. Symmetric is used for private key communication. Asymmetric is used for public key encryption. Symmetry. In symmetry, when you look at a circle, this one is the same as the other end. It's symmetrical, but in asymmetrical means that one is different from the other. Okay, so in asymmetric encryption or public key encryption is what is used for the initialization of the communication. How to once you want to initialize your communication with the service securely. Once you've initialized and you have agreed on a common secret key, every other communication that you'll have with that service will use the secret key. The public key, you use it once. The private key, now you use it continuously. Now here's the difference about public key. In the public key, the best approach people have used is prime numbers, using prime numbers. And prime number factorization is the method that has been used to share public keys. But in private keys, you can just generate it at random. You can generate a random key at random and then communicate. Okay. So in public key, the approach that the algorithms that generate the public key, they generate prime numbers. It uses mathematical formulas to generate prime numbers. And for private key encryption, it just generates the key at random. Okay, it generates key bytes at random. So block ciphers, I've discussed block ciphers, stream ciphers, symmetric algorithms, and now there's this one here we call reversible ciphers and non-reversible ciphers. Reversible ciphers are the encryption algorithms that people can use to encrypt and decrypt. You use the same algorithm to encrypt the data and to decrypt the data. You can be able to generate the plain text, okay? And that is those are the main algorithms or the main systems that are used to encrypt files, any type of data. But non-reversible ciphers, those are ciphers that you can, once you encrypt the data, you cannot reverse the process to get the original data. In reversible, you can reverse the process to get the original data. In non-reversible, you cannot. You can encrypt anything, but you cannot reverse the process to get the original ciphers. And examples are like for the reversible, those are the common encryption algorithms that you use. File encryption algorithms, RSA, DES, even elliptic curve, you can use it. You can use that to encrypt data to reverse because you're reversing a limited size of data. For AES, you're encrypting large volumes of data. A 5.1, you're encrypting streaming data. But for non-reversible, you use something like MD5, SHA-1, SHA-256. Now, that data, the output will be data of a limited size, a limited fixed chunk, limited size of data that you cannot be able to reverse back and get its original data. We're going to do a few examples here. Now, we've discussed private and public key as an example. Now we've discussed hashing functions like MD5, steganography. Now, the history about steganography, what used to, I think it was during Caesar's time in war, there was a problem whereby when you send a messenger, when Caesar sends a messenger to one of his generals at a far distance, the messenger could either give the information to the adversary, to the enemies, or they could be intercepted by the enemy and the message read. So by the time it reaches the general that is far away, the enemy already knows what is happening. So in order to hide that information in a way that they cannot know even whether the messenger has that information. By the way, when it comes to cryptography, yes, you know this information, this is the information, and it's hidden. You cannot tell the way it is. But in steganography, you don't know even if there is information, you do not know. So what they did is that they shaved the hair of the messengers. Once they shaved the hair of the messengers, they wrote the secret message on the scalp of the messenger. And then they let the hair grow. Once the hair grew back, now they gave the messenger a fake message to go now to the enemy, to the generals, to the generals who are positioned far away. So when the enemy intercepted the messenger, the enemy could read the message that the messenger is carrying and get wrong information, but not knowing that the true message is hidden on the scalp of the messenger. So once the messenger reaches the destination, the messenger is shaved and the general receives the message as is supposed to be and securely. That is pretty much the history of steganography. Now, digitally, nowadays when it comes to application of steganography, you can hide messages. Hiding information, you hide information in plain sight. You can hide it in images, you can hide it in audio, you can hide it in even plain text files whereby it whites out. But we're going to see how steganography applies when it comes to images. Even in text steganography, I'm going to show you using an example of some code I wrote here when it comes to text-based steganography. Now, private key encryption, as you can see, in private key encryption, you have the plain text, you have the encryption algorithm. The key that is used to encrypt the data will be the same key that is used to decrypt the data, okay? That is pretty much private key encryption. But in public key encryption, you have the plain text and you have the key that is used to encrypt the data, key one. Now, this key one is the key that is shared to the public. All you can do with that key is encrypt the data. You cannot decrypt the data. Now, once the data has been encrypted, the person who is supposed to receive that data has its corresponding key, the key that matches the key that corresponds to key one that is used to decrypt the data, to convert the data back to its original state. Now, that person will use the same algorithm or a different algorithm slightly modified using key two to decrypt the ciphertext back into plain text. And this is what happens. This is the key. For example, this is the secret I want to share between, this is a secret padlock and a secret key that I want to share between me and Jones. I use Jones' public key to hide it in a box. And then whatever will come out here is a locked box that contains that padlock that I want to use with Jones and a spare key. And then once Jones receives that box, what Jones will do, he will use his own other key to unlock the box and get the padlock and the spare key that I sent him. Now, going beyond that, now anytime I want to communicate with Jones, we are just going to be using the same padlock, using the same key. I have the same key, Jones has the same key, and we are using the same padlock and we're communicating. Do you understand that analogy? Is that analogy clear? Guys, I need your input. Is that analogy clear?
Yes, it is.
Thanks. Nice. Now let's go to steganography. And as I've explained, steganography is just hiding information in plain sight. Okay? You hide a message in another message. You can hide it you can hide text message in an image. You can hide it in an audio file. You can hide it in a video file. You can hide it in in another text file. Okay, I'm going to show you an example of what I did. Now, hashing, hashing, first of all, is non-reversible. It's of a fixed size, and it's used for password storage, and it can be used, it's also used for file verification. Now, remember in the previous slides, I described that in order for us to authenticate that a file has not been altered or has been altered, we hash that file, we generate the hash of that file, and compare it with the original file that has been sent or from the original source. If the hashes match, we know that this file has not been altered. But if they differ, we know that this file has been altered. That's why when it comes to downloading files, the file, especially software, when you look at online softwares or online sources where you can download software, you are also provided with a hash, so that once you've downloaded the file, you compare whether that file itself that you're downloading, that software, has been downloaded completely and successfully. You compare the hashes of your local file with the hash that is on the remote source. The problem is that it's prone to attacks, and the reason as to why hashing is prone to attacks is primarily because of this, the fixed size. Assuming like this, we have a file, we have a hashing algorithm that generates an output of 4 bytes, only 4 bytes. What are the chances of us having different types of data generating the same hashes? Is it low or is it high? And I need your interaction. So
It's high.
It's high. It's the chances of finding the same hash for different sources is high. Now, what happens is not that for us to increase the security of a hashing algorithm, we increase the size of the output. Okay, if it's 4, you can get 16 combinations. Okay, if it's 2, you get 4 combinations. Can you see that when we increase the size of the output, then the chances of us getting the same hash for different inputs is inversely proportional, or it decreases with the increase of the input size. And that's why we use password storage for the files. Now let's go to format preserving encryption. Now this one here, this type of encryption is whereby the input, if it's 10 characters or 10 digits, the output will be an encrypted form, but of 10 digits. So if you have if you encrypt a file using format preserving encryption, you preserve the type of character set and the size of the file of the input data. So if the character set is only digits 0 to 9, the output should also be 0 to 9. If the size of the characters should be 8, like your identification number, the encrypted data should also be 8. The reason as to why format preserving encryption is used is because when it comes to the encryption of data, there are some systems, like legacy systems that have been developed years ago. And once you develop a system, you develop an old system and you modify the system, try to use later technologies, but you want to encrypt it, you want to secure the data. The database, the way the system the way the system processes that data, or the way the database stores the data, will also dictate on how you present the data. Now, this is an example. There is a certain bank that was back in when was it? Was it? I think it was 2013, 2014. So what they did is that they upgraded one of their systems. Once they upgraded one of the systems, the database, the system needed to use needed to encrypt the data. But unfortunately, the data source, the database, the data, you could not be able to manipulate it, because it used also some the way it was defined on the old system is what it used numbers. The character the what do you call it? The format, the type of data format was fixed. It could not be manipulated. So in order for them to use the same system, using the same data, they needed to find a way in which they could be able to encrypt the data, but still maintains the data's format. That is where format preserving encryption comes into play. So some encryption tools are things like LastPass, BitLocker, VeraCrypt, FileVault, 7zip. These ones, you can all Google them and you can download them. All of them are free. All of these file encryption systems, encryption tools are free. You can download them over the net. Now, for email services, encrypted email services, there is Proton Mail, Tutanota. Now, in encrypted email services, what I mean here is that the data that is stored on their servers is encrypted, so that even the only person who can be able to read the data in plain text is you. And the key is stored in a way that once you log in, the key is used to decrypt the emails and provide the email results to you. And one of the things here is that the encrypted email services, they are not that fast. You'll notice that they have speed issues because of encrypting emails on the go, on the run. Emails like Yahoo, I don't think they're encrypted. If you gain access to those servers, you can be able to read all emails. Even when it comes to email services like Zimbra, you go to the database, you see all emails in plain text. But for encrypted email services, the database, the records are all encrypted. The database, the email database is encrypted. So the only person who has the key is you, the client, okay? So the system admin cannot be able to read. The free email services, actually I've used Tutanota. So Tutanota is one of a recommended email service you can use. It's free of charge for a limited amount of emails. For any email or file size greater than that, you need to pay, and it's secure. You can use it. Now, encrypted messenger apps. There's WhatsApp, Signal, Telegram, Viber. Now, these apps use end-to-end encryption, and here's one way that applies. Let me give an example when it comes to end-to-end encryption in terms of apps and through the browser. Now, when it comes to the app, the decryption key, you have your own encryption key and decryption key in your app. I'm just explaining it in a general approach. Now, your app, if anybody wants to communicate with you, or any contact wants to communicate with you through your WhatsApp app, what will happen is that your app will send that person's, for example, let me use an example of who else wants to be used as an example in this session? Anyone?
You can use me as an example.
Okay. Now, for example, I want to communicate with Terry. Terry has WhatsApp. I have WhatsApp. So, in order for me to communicate with Terry, I'll send my WhatsApp will send, because I've already saved Terry's number, and I want Terry to add my number. I'll send Terry a message. My WhatsApp will send Terry a message containing my public key. Okay. Once Terry receives that public key from me, Terry will generate a private key that will be used between me and her. And then WhatsApp will encrypt that key and using my public key, and then it will send it back to me. Now, once I receive it, I'll decrypt it using my own private key and then confirm to Terry. I'll send Terry an acknowledgement that this is the key that you've sent me. I'll encrypt it using her own public key. Once I send that, I send the confirmation, the same key and the confirmation that I have received this key. Once Terry decrypts it, she'll compare with the key that she originally has that is supposed to be used between me and her. Once she confirms that key is the one that's supposed to be used, then any other communication that we'll have will be using that private key. That's pretty much end-to-end communication via apps. Now let's go to browsers. Now, for the web-based end-to-end encryption, what happens is that you can send, for example, if I want to communicate via the browser, yes, Terry will have the same key. But in order for me to use the WhatsApp services over the browser, I need to have the browser send me the data securely. And this is what do you call it? It's away from, it's an extra security layer from the normal SSL. SSL just encrypts the traffic, okay? Now, once the traffic has been encrypted, nobody who's intercepting can be able to see it. Now, an extra layer is now in terms of end-to-end encryption. What happens is that WhatsApp will have a JavaScript, will have a script at the client end, and that script, what would happen is that it will generate a QR code, a key that will be used. I'll scan that key, and then once I scan the key, WhatsApp will tell me, yes, this is the browser that you want. This is the browser that you want to use, and this is the key that you want to use with that browser. So what will happen is that it will send encrypted data over a network, and it will be encrypted like twice. The first encryption is over SSL, the normal TLS SSL transmission. But once it hits the browser cannot be able to decrypt not be able to interpret the data to become viewable. It cannot be able to present the data. So what happens is that JavaScript that is loaded with the WhatsApp, that JavaScript will look at the session that is sent, the active session between that I've logged in with. And one of the fields in the cookies, for example, in the cookies, one of the fields will be the key, the encryption key. And then it will take that encryption key, take the data that has been sent at that moment, decrypt it, okay? Decrypt that data, and then present that data. What it will happen is that you send the data encrypted. You send encrypted data of an encrypted line. Once the browser receives that data, it goes to the cookie. It takes the encryption key from the cookie, then uses a JavaScript to decrypt that the encrypted data, and the decrypted data will be a HTML, just be either HTML formatted data that you can use, you can view on the browser. Okay, that way, once you send the data, when I want to send when I want to chat or when I want to send data over the web, it will also encrypt it, and then the service at WhatsApp will be before the current version of WhatsApp, it will send it to my phone, and then my phone will now send the data over to the client as it's supposed to be done. Or the functions can be over the client, the keys can be over the client, the browser client. So that is one way in which end-to-end encryption can work. You have an encryption script, you have an encryption script or like JavaScript, and that JavaScript returns a specific page if it cannot decrypt data. But if there is a session key, if the cookies, if the cookie has an encryption key within it, then the JavaScript will pick that cookie, that encryption key, and then encrypt the encrypted data that it has received, and then translate the data into HTML formats that you can be able to see on the browser. That is one way in which you can be able to implement end-to-end encryption via the browser. So, is that okay?
Yes.
Okay. Now, in digital signatures, I'm going to show you how digital signatures work. We're going to pull a simple digital signature from a website and see how it works. Now, as you can see, a digital signature is a mathematical technique used to validate the authenticity and integrity of a message, software, or digital document. Now, sometimes digital signatures can be appended data. For example, if you have a file and there's extra data, that extra data, once you decrypt it, it can be able to tell you that the source of this data is so and so. That's why when it comes to digital signatures, especially when it comes to browsers, it's not just anybody who can decrypt the data. It's to whom the data is supposed to be decrypted by that they can be able to decrypt the data and verify the digital signature. The digital signature just gives the ID of the source of that file. Okay, let's define it. Let's define things as files. You have a file. I want to send the file to Terry, to Tracy, or Tracy. I want to send the file to Tracy. So what I do is that I append my information that this file comes from Mike, is sent at this date, at this time, and I am the owner. And this is the secret this is my secret. So once I encrypt that file, Tracy has a way to decrypt the file. Once Tracy decrypts the file, she'll look at the end of the file and notice that there is extra information. Once she extracts that extra information and decrypts it, she will realize that, but this extra information says that this file belongs to Mike. Okay, that's like a signature I've appended on that file and I've sent it to Tracy. That will be used to verify my identity. That's pretty much it when it comes to digital signatures. You append your identity and encrypt it. You can append it on a file. Now, in one-time padding, what happens is that sometimes you might want to use a key once. Maybe very highly sensitive communication or information. You want to use a key once and you're done with that key. You discard it. That key cannot be used again. In order for you to do that, you can use something called one-time padding. This is whereby you have a key, you have data of size X, and then you generate a key of the same size as the data, then you XOR that data. But when it comes to XORing is one of the most, actually, I think it's I believe it's the most secure approach right now when it comes to encrypting data, because it's the primary approach when it comes to, it's one of the primary primitives that is used to secure, to create cryptographic functions. And it's also, amongst them, I usually find it as the most secure from handing in. But when it comes to XOR, these are digital, what do you call it? Digital logic Boolean operations. There is OR, there is AND, there is NOT, there is XOR. And this is how it works. In OR, the data will be, the output will be true if one of the inputs is a true. Okay? If you have, for example, if you have two inputs and one output, the output will always be true if either one of the inputs is true. In AND, the output will only be true if and only if both inputs are true. The problem with AND is that in OR, you can try to see, actually OR and AND is very difficult to reverse the process. That's why you can use OR and AND in order to create hashing algorithms. And not just use one input and you negate it. If it's a true, the output will be false. If it's a false, the output will be true. Okay? And then there's XOR. XOR, if the inputs are not equal, the output should be 1. So if input A is 1 and input B is 0, or input B is 1 and input A is 0, the output will be 1. And that is how XOR is used when it comes to outputting the data when it comes to encryption. For XOR, you can reverse the process and get the original inputs. For OR and AND, it's not in some cases it's yes, it's possible, but if the inputs are different, okay? Yeah, if they actually, or it's not that, I don't think or is that possible, but and I'm sure and is not possible to reverse the whole process, because in and, if the inputs are 1, if both inputs are 1, it produces a 1. If both inputs are 0, it produces a 0. If either of them is a 0, it produces a 0. So it will be difficult to know which one, whether it's input A that was a 0 or input B that was a 0. And that applies. That also applies when it comes to OR. But in OR, it's there are some cases you can be able to tell if the inputs are different. But in AND, you cannot be able to tell. It becomes difficult. That is why you can use AND for hashing algorithms, whereby hashing algorithms are non-reversible. Now, this is an example of what I've discussed here. You send public key for A and then public key for B. Can you see this? These are two forms. Send public key for A, send public key for B. Send encrypted private key for A and send a message using the private key for A to confirm that, to tell A that this is the private key Manipatia. This is the private key that you've given me. Is it it? If phone A verifies, then every other communication that is conducted between these two will be using the private key, the shared private key between these two. Now, in centralized decryption or encryption, this is now when it comes to server-client encryption. You have different clients communicating with the same server and encrypting the data over the service. Steganography just, when it comes to steganography, you have information and you alter the color bit information of each of an image, of each pixel of an image based on the inputs that you've been given. Let me just proceed so that you can be able to see how it works when it comes to examples. So for blockchain, as you can see, in blockchain, what happens is a growing list of records called blocks that are linked together using cryptography. And this is whereby you can have one record that if you alter the record, you use the same key and you add new data to create a new record which can be traced to the previous record. And one of the best approaches here is when it comes to maybe land. In land, there is the original title deed that comes from the government. Now, once you send that land, the title deed can remain the same, but there can be a key there can be a key that can be traceable to the original source. So once the land has been sold or a logbook has been sold to multiple users, to multiple owners, you can be able to tell using that key, not even by searching, but you can be able to compute the origin, where it started, who was the first owner of that vehicle using the logbook, or that land using the generated key in that title. And it's also used, as you can see, when it comes to finances or financial consensus-based finance or transaction. Ethereum, Bitcoin, they are the most popular in application. They're the most popular approach, the most popular cryptocurrencies. And by the way, one of the things that pisses me off is you can hear people calling themselves crypto. And when you have a discussion with them, you realize that they are not cryptographers per se. They just delve in cryptocurrency. They trade in cryptocurrencies, which is misleading of the word crypto. If it's supposed to be crypto, they are supposed to specify that, yes, they are crypto for cryptocurrencies. They trade in cryptocurrencies, not crypto. They create blockchains or they create encryption algorithms. So that is what I mean by that. Now, as you can see, the use of cryptography when it comes to ransomware. But one of the creative approaches I've seen when it comes to ransomware, especially when it comes to Android ransomware, you find somebody creating a ransomware where it sprays, it changes, it divides the data into chunks, and then encrypts different chunks of the data, different sections of the data using the ransomware key. Once it decrypts like that, it reduces the amount of time that is needed to encrypt the whole file. In some cases, for very effective ones, it encrypts the whole file. But for others, it encrypts different chunks of the data. Now, there's something I've not included here, but let me explain it. There's something, when it comes to application development, especially when it comes to license-based application development, one of the approaches I used when it comes to creating licenses for applications like in Android, and I'm going to use one that I developed recently, was if I want to create a license for an app, if I have the license sent from the server, what will happen is that you can be able to send multiple licenses from the server and get the way the license will be generated. If you have for example, a mechanism whereby there's a formula in which the license has been generated from the app, and then the license is compared using the same algorithm from the server, what will happen is that a reverse engineer will be able to tell how the algorithm has been designed, determine how the license is generated, and then generate a bunch of licenses for your app and give it to the people for free. Now people will start using your app for free. The approach that I used was I have the license generate at random, then the license is sent to the server, okay? Is sent to the server, and what is stored in the app is not the license, is the hash of that license. So you generate a license from your app, send the license to the server. What is stored in that app in terms of, like for example, in Android, the shared preferences, what will be stored is the hash. So if somebody tries to reverse engineer the app, they will have to they'll have to either replace the hash with their own, or they will have to figure out how the hash works. And the license will be timed. So after 15 days, if the license has not been triggered, if the server has not sent the same license back to the app via a license activation function, the app will lock itself. It will disable many functions. So that is an approach that I used recently for a certain app that I worked on. You generate the license you generate a random license. You send the random license to the server using a post when you're registering the app, when you're registering your profile from the app. Then once you do that, you what will be stored so that which will be used later for the activation of the app will be the hash of that license. So once you try to activate the app, even when you're looking at the app's data, you cannot be able to tell that this license belongs to this app. This is the way the app generates the license. You cannot be able to tell in forehand. But when it comes to reverse engineers, once they reverse a file, that's pretty much it. They can be able to do almost anything with that application. So now in quantum cryptography, the future of cryptography, what happens is that now you're using quantum computing technology in order for you to be able to create cryptographic algorithms to secure transmission of data. One of the premier encryption algorithms, actually it's a protocol, was called the BB84. And the BB84 worked on percentages in terms of when you send the data, the service, the client doesn't send the whole key. It sends a part of the key, and then the server will compare what percentage of that key is accurate. If it's above 70%, then they can have a consensus that this data, this key that the clients what I'm sharing with the client is the key that is being used, and then they will proceed communicating using that key. The approach is pretty novel, and it's pretty creative when you see the approach itself. And the purpose of the BB84 was because in quantum computing, the application of the Schrödinger's equation for prime number factorization introduced a major threat in public key encryption, especially when it comes to RSA and elliptic curve. And RSA and elliptic curve, their security is based on how fast you can generate a large prime number, like a prime number of maybe 4,000 digits. Okay, a prime number of 4,000 digits. Before quantum computing, it has always been very difficult. It takes even a lifetime for you to develop a prime number to factorize. You have one prime number, to see the corresponding prime number that can be used by that prime number to generate the plain text or to decrypt the data can take a lifetime. But using Schrödinger's equation, it reduces the required number of steps to generate that prime number. So that's where the quantum computing introduces a threat to cryptography. It introduces the threat to cryptography specifically toward public key encryption. And the public key encryption is the backbone behind all forms of communication, because you need to share secret keys before you can start communication. And in order for you to share secret keys, you need to You need to You need to find a mechanism in which once you encrypt the data, the other person can be able to receive the data in a way that even if I give you a key, you can only encrypt it, and the key can be intercepted by the public, but the resultant encrypted data cannot be broken. And prime factorization and prime numbers worked well with that. But in quantum computing, the number of steps that are used to generate prime numbers in terms of prime factorization, you have this prime number to find its prime factor, the corresponding prime number factor has been reduced, will be reduced. I'm not so sure whether it has been fully implemented I just saw a few things, but I'm not so sure. I cannot say for sure whether it has been implemented currently, but that is a major problem. So when it comes to attacks, there is the ciphertext. Ciphertext and all attacks is you have ciphertext, you have a lot of ciphertext. You try to brute force them and see whether you can be able to get the plain text out of the ciphertext. Non-plain text is that you define the plain text that you want to use, and then you try to compare the output of that encryption algorithm, whether there's any ciphertext that has been generated that corresponds to one of the plain text that you have, or the plain text that you've provided. If you provided maybe your name, let's say Peter, and then you encrypt it using the cryptographic using the cipher system in terms of a black box approach. You try to see whether the output will correspond, which of the outputs, once you alter the keys in each step, whether the output will correspond, whether one of the outputs will correspond to the plain text that you provided, plain text that you have, and then there's actually the non-plain text. You knew what you know what the plain text looks like, and you know what the ciphertext looks like, but you want to see whether you want to see which one corresponds to which one at each stage, because if you know the plain text and you see a bunch of ciphertext, you'll try to figure out which one of these ciphertext corresponds to that non-plain text that you have. Chosen plain text is you who defines it. I'm sorry, I meant to say the chosen plain text is the one that you define the plain text yourself. Chosen ciphertext is the reverse versa of chosen plain text, whereby you take a specific ciphertext that you want, and then you try to see what plain text will come out of that plain text attack. And in most cases here, when it comes to MD5 or when it comes to hashing, see, when you go to hashkiller.co.uk, you can use the chosen ciphertext and try to see whether there are plain texts. There's a corresponding plain text from that website. Okay. Man-in-the-middle attacks. This one has multiple ways in which you can be able to try to attack it, and most of the times is you can try to use session. You can try to generate your own keys and try to see whether you can inject your own secret, own private key, and it can be accepted as the server's private key when using man-in-the-middle attacks. Side channel attacks. Side channel attacks have not reviewed it a lot, but most of the times, as you can see, it usually looks at how the processor, when it comes to the processor responding, whether you can be able to pick out different digits or different characters from the processor's cycle or oscillation cycle, and be able to map the oscillation cycle to corresponding data or to specific data or keys. For example, when you want to encrypt the data, you have the processor. You can add sensors to that processor to listen for raise in oscillation values, and you can be able to tell this processor, when it comes to an A, this processor will the cycle. This is how it will respond. So when you're listening at the processor or the system, you can be able to map with higher accuracy levels on what the encryption key that has been generated based on how the processor oscillation increases, and how the feedback. This one I'm not going to tell you about this one, because this one it's a pretty complex approach, especially because it requires some hardware, and the researchers that I've seen that work with this work with very sophisticated hardware. Brute force attacks. Brute force, you just try every possible combination. Okay. Birthday attacks. Obviously, you try to use like birthday information to be able to try. I've not seen this one being applied a lot, but brute force is brute force. People try to use it, and using known plain text attacks. You generate several keys. Try to compare whether you can break that key based on like a password, like password cracking, by using something like John the Ripper. you can be able to try and see whether the password stored, the encrypted password hash that is stored in your machine corresponds to the same password that has been provided in one of the passwords that has been provided in the key file or the word list. So as you can see, this is the man-in-the-middle attack. I've talked about it briefly. And now when it comes to cryptanalysis, the number of keys, as you can see, the bits, this is the bits, the size of the key, and the number of keys, the number of possible keys, the key space, how long it will take to crack, to generate all, or to compare all the possible key combinations with the maybe key combination the key that you want to compare it with. Okay, 56 bits, the number of keys, and by the way, this one will reduce based on the processing power of the computer that is available. In quantum computers, this one really doesn't apply, because in quantum computer, what it looked at was prime factorization. That is where I've seen there's a lot of promise in terms of cryptanalysis, especially when it comes to cryptography, when it comes to quantum computing in prime number factorization. Okay, there's a type of quantum computing, RSA breakable, quantum breakable. And as you can see, most of them use prime number factorization. Okay, prime numbers. When using prime numbers, the Schrodinger's equation can be used, the number of steps that are needed is less. So let me go through a few examples here. Let's do this. Let me start with what do you call it? Let's start with how you can be able to pull a server certificate. Now, before we do that, one of the reasons as to why you need to use a public certificate, not a self-signed certificate, is because when you're using man in the middle, using self-signed certificates, the end user who's supposed to use that system will not be able to tell with certainty that this certificate belongs to you, okay? Comes from the original source. That is the major risk. And the good thing is that browsers like Chrome, what approach they do is that they do not, first of all, allow self-signed certificates. They allow certificates that are signed from publicly signed certificates. If you want to generate your own public certificate, you can generate it free of charge using Let's Encrypt. But if you're using self-signed certificates, first of all, the Google browser will reject it. The other approach that browsers like Google have used that ensure the communication is secure is by comparing the domain URL with the certificate. Okay. So if the domain URL you have written at Google, maybe if the certificate says that, if the digital certificate says that the self-signed certificate is not google.co.ke, or it doesn't come from Google, and your domain, the URL that you've written is google.co.ke, if the certificate does not match, the Google browser will reject it outright, and it will inform you that that site, somebody is trying to phish your information. That is why you see sometimes when you try to use sites that have invalid certificates, or phishing sites, you realize that the browser will display a red page notifying you that this site is a phishing site, is a possible phishing site. It compares the URL with the certificate. It compares the domain with the certificate. And the other thing, it checks the certificate, the origin of the certificate. If the certificate has been generated by a non-legitimate certificate provider, then they can be able to tell you that yes, this certificate is legit, and you can use it. You can proceed using the site. Oh, and another thing, now when it comes to computer drivers, for those guys who write malware, like spyware, one of the things that they usually try to do is they try to have the application or the spyware run at the lowest level possible. And when it comes to Windows, drivers, when it comes to Windows, you can run drivers at a very low level with very high permissions and make sure that the driver, that application cannot be uninstalled, can run without being blocked by anything. So in order for you to write that, Microsoft, what it does, it restricts the access of those, or it restricts the kernel space access to only legitimately authorized applications, which include drivers. Now, there was this. I'm trying to remember. Who remembers the a case whereby the drivers that were built in Taiwan, the first thing that they did was that they stole certificates from the driver provider so that they could be able to generate their own certificate, own valid certificates for those drivers. They stole it from a driver manufacturer in Taiwan. Who can remind us on that? I'm trying to remember the type of malware, and it was a very famous one. Who can tell us? So let me do this. Let me just let me share a window. How come it's not displaying the terminal? Just a minute. Can you guys see my terminal?
Just the mouse. You can see a mouse
Okay.
hovering.
I'm trying to see how I can be able to. Okay, let's see whether. How can I be able to share my terminal? Let's see whether I want to share my terminal with everyone. Can anyone tell me how I can do that? I'm trying to look for. I'm trying to see whether I can be able to share my terminal. Is there a way I can share my terminal on? Because I'm trying to. Okay, do this. Okay. Try sharing. Yeah, I've tried. But when I click on this, all you guys can see. Okay, now assume, let's see. Let me share. When I share my whole screen, you guys cannot see it. Okay, I want you to do this. Okay, let me share. So let me try to use this and see whether it will work. Just a minute. I'm using Ubuntu.
So it's a common problem that seems to happen on Ubuntu systems where a lot of people have been complaining that they've tried sharing their screen and it goes blank when they're trying to share the terminal. Sorry.
Okay. So what I'll do is that I'll write the command and I'll have you run it so that you can see from your side what the output is, and I can describe it. We're going to use simple. We are going to use Google as the reference. So I'm going to write at the terminal open. Let's okay. Open. Okay, I've sent it. Okay, look at the side chart. I want you to paste that on your terminal. Oh, I've written it incorrectly. Make sure it's google.co.ke. Have you guys written it? If you write it on a terminal, it should give you, it should provide you with information about Google. Hello, have you guys written it? So you guys know that when you're browsing, it goes to, you usually browse via port 80, isn't it? But the certificates are usually exchanged from port 443, okay? The SSL connection, the TLS initial connection, so that you can be able to communicate securely. You start with the port 443, and then now the browser, anything that goes through port 80 will be encrypted using your what do you call it, private key, and the server's private key, the one that you have shared between you and the server. Have you guys done that?
Yes, I have.
Okay, so you can see something called begin certificate.
Yes. Kunam. There are two.
Yes. Now, good. Now, I want you to go down. I want you to scroll downwards.
Yeah.
Now you'll see something called written SSL handshake read 4306 bytes and written 384 bytes verification. Okay.
At the bottom of the after you
Yes, yes,
the server
yes, yes.
certificate information. Yeah, I can see.
Yeah. Can you see now something up now below it's new TSL version 1.3.
Cipher is TLS AES 256.
Yes.
Something. Yeah.
No, that is the one that the server will be using with you. Okay.
Yes.
So that certificate is the one that is shared to you from the server, and that is what you use to, what do you call it? That's what you use to communicate. The key, the begin certificate, end certificate, and the key itself will be shared through that, so that any other communication that comes to the browser will be any traffic that goes from google.co.ke via port 80 will have this information. So it will contain the information, the begin certificate and certificate. And by there, one of the things is that when it comes to increasing the security of any, what do you call it, any application, you need to understand that what do you call it? When it comes to sharing of certificates, or when it comes to securing your communication between you and the server, you need to ensure that the traffic itself, the traffic that is sent, the algorithm, the certificate that is sent from the app, for those who are creating apps, if the app is not that doesn't require that high level of security, you can use any certificate type. You can just send post requests using you can just send post requests using the normal HTTP request, HTTPS request. But if you're developing something like banking applications, you need to ensure that the security is as high as the security levels are higher. So you restrict the client certificate to only the app. You restrict the app to only allow specific client certificates. Now, before we proceed, you notice that when it comes to applications and authentications, we have passwords, yes, but passwords half-baked. A password is just one solution, and nowadays passwords can be broken. People can intercept your password, so you use things like two-factor authentications. But apart from two-factor authentication, you can use something like zero authentication, whereby you don't send the actual password or your credentials, and this is why. Now, for example, let's use an example. For example, the government website, where you get government services. So when you register for something like Huduma number, and you want to access other services from using your credentials, the Huduma number, what do you call it? What we assume. Okay, let me repeat it. Now, assuming you register your ID using the, what do you call it? You register your ID, your normal ID on the website, on the government website, the public,
eCitizen.
eCitizen, very good. eCitizen. Now, you realize that there are different government websites that can require you to log in using, to create an account. So in order for you to be able to log into those websites, you need to create an account with a username and password, but that one can be laborious to the user. So in order for it to be simplified, you can use zero auth authentication, whereby there's an existing service. And that existing service, you've already registered like eCitizen. When you go to a different website that requires you to log in, it can tell you, you can either log in using by creating a new username and password, or you can provide, you can log in via the eCitizen website. So you just log into eCitizen website. eCitizen website will send your credential, which will send your information, not even your password, just an information and authorization token to the site like, let's say Huduma number, okay? Or the department of what? You can use any other department. Can we use an example so that we can be able to see how things work? We can be able to discuss how things work. Which website do you know belongs to the government and is not connected to eCitizen? It's different. We can use something like for elections, okay?
Yeah.
Okay. Now, so you already have an account, you already have an existing account with eCitizen, but you want to log into, you want to create an account with maybe the IBC. Now, in order for you to create an account with the IBC, you can create an account by creating a username and password, right? But that you realize that this is a government, what do you call it? Government website. So the developers of that website, they can do this. They can collaborate with the government website. They tell the government, like, for example, eCitizen, do this, create a zero auth server whereby if anybody register, if anybody wants to register to IBC, instead of creating a username and password, they can just ask our website. They can log into our website, and then our website will send that information to your website, to IBC. eCitizen will send some information to IBC, including the names and the token, whereby IBC will now use that information to create an account for you and to allow you to access services from IBC. Are we clear to that? Are we clear to there how this works? Zero auth works. So let me show you using a demo. Okay, let me run it. Let me run the server. Okay, let me share it. So let me go to local 800, local host 800, 8,000. Now this is a login page, okay?
Yep.
Now that login page, you can enter a username and password, but you realize that there are certain services whereby instead of you to create your login credentials, instead of you creating your username and password directly, if there's another service that has collaborated that is willing to provide that information, to share that information with that website, you can say, for example, this one, you can say click maybe login via or sign up using something like Google, okay? And when you click on it, it will ask you, do you want to access your website? Now, do you want access to that website? Can you see what I'm presenting here? So there is confirm. Now, this one, as you can see, this one is not the same server. The other one was 192.168.0.1 This one is a different server. Can you see that? Now, what will happen is that if I allow, for example, this one is already logged in. If I click on confirm, what will happen is that it will take this information, the information that it already contains here, and pass it to the original server, which was 8,000. So click on here, confirm. Can you see this token now?
Yes, I can see the token.
Let me increase it. Can you see that?
Yes.
Now that access token, this access token and refresh token, this one is what will be given. As you can see, what has been provided, the scope that I've used. These I've used, what do you call it? I've just used simple Flask application. I've used a simple application. I've created a simple application for Flask using clients and the server so that you can be able to create your zero op and be able to log in to that. For example, if you have a website B, like IBC, and you already have your credentials registered on eCitizen, you can sign in or sign up to IBC via eCitizen, and that is how Google usually works. Okay. Once you sign in on that, once you sign in using that, say now this token that has been given here will allow you. Now, what do you call it? Now once you go to, as you can see, you're in localhost 8,000. This token, now this is what is going to be given to you. This is what you're going to use to access the services. Okay. To your user, this is what your user profile will be used to access the services on that site, like a normal user. That is how zero auth works, and that is how it works using tokens. So I can, once I come here, I delete these and I try to access it. It already shows me I'm already registered. Can you see that? I have an active session.
Yeah, let's see.
So if I want to log out, all I have to do is just write that log out, and everything goes back to the way it was. So if I click on it here, let's see now. Let's see whether I have another script that I used. Okay, just a minute. Okay, let me run this one. Oh, let me close. Different, stop all, and then main. Oh, sorry, let me see where. Oh. Let me show. Just a minute, I'm trying to modify some of the functions here. Okay, let me use this one. Let me run it. Just a minute. If you have any questions, please ask so that we can proceed as I'm explaining. Okay, let's see. I think what I did here was so now, okay, let me just get back to where it was. I'll upload the code on GitHub, but it's the principle behind it The principle behind this concept is that now here, when you click on it, for example, if you're using Google as the third-party application to give you access to, you can just click on it and it will ask you, do you want to log in via Google? That's pretty much zero authentication. And in zero auth, what happens is that you don't provide your password, okay? You don't provide your personal information. You only ask a different website to give that site access to you, but it gives a token, okay? It gives a token for you to be able to access its services. Not the username, not a password. It just gives a token. And it ensures that the amount of information that it gives the other website is limited, and it's only the ones that is needed by that website. So the other website might not even have your password. You cannot even have a password with the other website, but you can be able to access services from that website. Now, recent developments when it comes to recent developments when it comes to recent developments when it comes to multiple two-factor authentication, or hiding of identities. This is what I noted. Now, in cryptography, people hide things based on three scenarios. The first one, you can hide communication, you can hide your identity, and you can hide whoever you're communicating with. Okay, three things. You're hiding your communication, you're hiding your identity, and you can hide the person or the person you are communicating with. Now, when it comes to PKI, public key encryption, in order for communication, if you want to hide your communication, you just encrypt it in normal encryption, SSL, TSL. By hiding the person you're talking with, you use things like Tor, okay, onion routing, whereby you create a service. That service, every request, if you want to access a service that you don't want anyone to know to be able to access or know you're accessing, you can just channel it through a private VPN, okay? And that is how VPN works. You encrypt the data that you want to communicate, but you also ensure that the requests from your server do not directly point to that service. They point to a different server, and that server will be the one that decrypts it and understands, yes, you want to communicate with server X. Now, when it comes to encrypting your identity and the person you're communicating with, one of the challenges that was identified was when it comes to communicating, the people who provide access to servers like WhatsApp, they can be able to intercept your communication. Not the actual messages, but they can be able to tell from their logs who you are communicating with. Now, in order for a person to solve, what do you call it? For a person to be able to hide the communication itself, you can be able to use PKI between individuals to change your identities in a way that you change your identity, you send your new identity using PKI to your contacts, and when your contacts want to contact you, they will contact you using your new identity. It's like this. Assuming I'm communicating with Tracy, and then I change my name, I'll find a way to send Tracy information that my name has changed without anybody else knowing. So when Tracy wants to communicate with me, maybe I changed my name from Michael to Martin. Tracy will always address me as Martin. But the people who have been observing our communication know that Tracy was used to communicate with Michael, but they cannot be able to tell whether whether I'm the same Martin whether Martin is Michael, the Michael who she was communicating with. Now, when it comes to that, in order for you to secure that communication, the reason as to why that is a necessary approach is because you can be able to create patterns between people. And those patterns will tell you that, for example, Tracy has been communicating with Michael at this period. Even though you cannot know what we have been talking about, you can be able to tell how frequently we have been talking together, the times we've been talking, and even my network. You can be able to identify my network. So one of the reasons was one of the recent researches I've done was in this. Let me just share the topic, and from there you can ask any questions, and we can use a few minutes for me to answer some of your questions. Let me just get the data. Just a minute. Actually, I used GitHub. I stored it on GitHub. Let me share the screen. Oh yeah, it's shared. But if you want to look at some of this, if you want to look at how steganography can be applied, you can use this one. This one, randomized substitution cipher. You can check it, you can download it, test it. Another one, where is it? Let's go to repositories. Now this is public information, so you can be able to view it. Now this was one of the papers that I worked on that was supposed to help you hide your identities. So the main approach behind this was your identity changes, but you can still be able to maintain communication with everybody you have been contacting. So the initial findings that were there was that, as you can see, this one is MQTT. When it comes to MQTT, you can be able to create logs as the administrator of that server. I can be able to log everything, log all communications between different users, and you will not be the wiser. Even if you guys, what do you call it? Even if I give you guys terms and agreement or privacy information saying that I will not log anything, I can log and you guys will not be the wiser. I can log everything because it's on my side. So that's and this is an MQTT message, an example whereby, yes, I cannot tell this data, what this data means, but I can be able to tell who I have been communicating, who Alice has been communicating with, okay? And when you do that, now you can create algorithms or AI systems that can be able to, that can be able to create a pattern of both your networks and chatting activities. So if I want to profile you, I can be able to tell you have been speaking to so and so at this is your network, and these are the people you have been communicating with, and this is how frequently you have been communicating with, and the times you have been communicating. So I can be able to tell, I can be able even to create a profile about how you've been communicating with others. So in order to secure that, your communication, especially identities, this was an approach that I was working on in order for you to create, for you to hide your identity, to change your identity, but still maintain communication with all your contacts. Now, welcome. I welcome any question, any and every question you guys might have. Questions? But if you want to test anything else, you can use tag hide. You can, for steganography, you can use tag hide. Let me just share the screen. This one, tag hide. And the documentation is pretty simple. Tag hide, embed the picture that you want to embed and the text file that you want to embed. Okay? And if you want to extract the data, you just select tag hide extract SF picture.jpg. it's pretty trivial when it comes to how to use it. Also, when it comes to, let me do this. Let me share something that if you want to get your user password. Now, a few months ago, what I discovered is that there are certain services, local services, that send you PDFs of your transaction updates. Now, those PDFs are locked with keys, are locked with passwords, and those passwords are your ID numbers. The problem is that even if it's your ID number, you can be able to generate all ID numbers, the range of ID numbers from the first person in Kenya to the last person in Kenya, and the amount of time it will take for you to crack any PDF document using the ID numbers will take about 5 minutes max using a normal PC. So ID from ID 2 something to the last ID, that you can be able to crack them. And I tweeted it, I think, a long time ago. So let me just share with you something you can be able to use on your machine. See whether you can be able to extract you can be able to brute force your password, your PC password. I've sent the command over the side chat. If you have any questions, you can ask.
I have a question about steganography.
Yes, do ask.
Yes, I came across an audio file